Well, welcome everyone to that Minisymposium, and I'm happy to be to open this exciting session. So what I want to kind of share and discuss a bit today is somehow scalability and kind of HPC readiness, let's call it like that, on Julia's GPU stack, targeting supercomputers, and in particular, like the kind of latest generation of supercomputers that also made it to the exascale, which are powered by AMD devices, so AMD GPUs. And I hope that, with what I'm gonna cover, I kind of feel that's really important, because that's also where Julia for HPC, I guess, can stand out compared to maybe other approaches in terms of, I'd call it portability in many ways, but hardware portability, but also kind of development portability, like two-language barrier that can be overcome and that one can basically rapidly prototype and port kind of research code, not community software, like research code targeting specific problems, in a pretty efficient way to deploy on supercomputers, and not on only one type of architecture, but also on different type of architectures, which is like, NVIDIA, AMD, soon Intel, and who knows what comes later, maybe IPUs like from GraphCore, and so on. And I guess that's really, I really kind of see that's one of the key and the power of Julia there. So before kind of diving some technicality, just quickly, what do we do? So I'm kind of working for now in the glaciology lab at ETH Zurich, and where we're working on a piece of software that's called Fast Ice. And guess what? It's to model ice flow. And now we just got kind of extreme scale European grant to try to simulate and understand. So what you see here is the ice flow speed over Greenland. Where it's red, it doesn't move. Where it's red, it doesn't move, and where it's kind of purple, it moves like at meters to kilometers per day. And those are called like those things here. They're called ice streams, and basically that's a big problem. So if we kind of don't account for the ice melting because of the sun, so kind of the ice flowing out of the ice sheet, it's kind of 99% flows out through these couple of streams. And we see them, but we still don't understand why they appear here and here, and why there are maybe only 10 of them, and why not others, etc. So for this, one needs some advanced modeling, and we were granted about 5 million GPU hours on Lumi supercomputers, so like the little replica of Frontier, that kind of still makes it number 3 in the top 500. And one important part is to run forward models, but ideally we also want to make UQ and inversions, etc. So why we do it is kind of this: we zoom in one of these streams. Basically, you see that where it's here, where it's red, it moves fast, so it's kind of viscous fingering, and where it's blue, it doesn't move. And then you have this shear margin, like this region where you have extreme shearing, and kind of you can imagine if you shear thing fast and heats up, it melts further, etc. So they're pretty much nonlinear interaction that one would need to resolve if one solve this, try to get a numerical model to resolve this. And also not only at the streams, but at the bedrock. So that's the other picture. So basically we want to understand why kind of, or we believe that kind of the roughness of the bedrock would further kind of lead to localization. And then one need to resolve this in 3D to understand where one gets localization of flow and where not. So how we do it, we kind of developing full Stokes models, so kind of no rocket science, but kind of, let's call it classical HPC, but with kind of new tools. And we kind of still develop some, try to come up with kind of iterative solvers that can leverage parallelism of GPUs and multi-GPUs. And we also can account for these different boundaries. So there are some preliminary results, for example. So here it's just a synthetic where we're testing something. So that's kind of a valley with a bumpy bed, and the arrows are the ice flow velocity. And if I kind of play that thing, we'll see that kind of if there is forcing over time, it would speed up, and then it would start to create at the very end some lenses, and this is contours or these lenses that come, this contour where basically there is kind of this shear heating going on, so where would get like kind of melting of the ice and rapid like runaway, and that's kind of shown here in red. So basically, that's those kind of things that we want to resolve at kind of physically 10-meter scale over entire Greenland, and that's what we need a supercomputer. So how we do it? So we kind of took the choice to give it a try and like proposed and got funding for that to use Julia and AMD GPUs on Lumi. So I guess we're the only project doing that. Yeah, so the cool thing, as I said about Julia, it's kind of, we can come up with tools to try to support this variety of backends, maybe threads, multi-threading, like just threaded threads, for example, but then also CUDA, and now AMD GPU, where I was a bit more involved, and there also have to kind of, that was work we started also with Julian Samru, and now Anton Smirnov from AMD proper, who helps and kind of takes a bit over the AMD GPU stack, and kind of we managed to get that package that was just getting started somehow closer to the standard, and like kind of getting more and more towards what CUDA.jl sets up, with NVIDIA being around for many years. And where Julia is really important there is one can really try to have, or how we try to come up with the thing is come up with a single code base that can leverage all the different backends, such that, well, we can just upon changing a single parameter, just make that the entire stack would kind of, yeah, run and become basically deployed on a different architecture. And what we also want, so we want to be able to leverage like this portability that Julia offers to have like prototyping. I mean, I'm commuting to work, so I usually work in the train, try to run my thing on my little computer in Flow32 on the M chip, and then while I want to kind of try it in 3D, etc., I just kind of connect to the supercomputer, and then I scale it up to thousands of GPU, and kind of that's the thing that that simplifies my life as a researcher, and so we'll try to make that happen. And yeah, on the sensitivity analysis part, so for those huge 3D simulation, you cannot afford like MCMC and other things because there's just too much dimension. So there we kind of now try to leverage AD and gradient-based optimization, and well, that was the topic of the workshop that we gave on Tuesday. So how to make this scalable, parallel, etc. So yeah, just a simple, so kind of we developed some tooling around the backend abstraction, and here I just highlighted, so that's kind of an explicit diffusion code here, written using parallel stencil, one of the packages we develop. So it supports stencil, like there's a way to write stencil operation in a math clause formulation, supports our backend. So here, when we init parallel stencil, we can pass the precision, the number of dimension, and the backend, so threads, CUDA, AMD GPU, Metal to come at some point. And yeah, recently added also AD support. And so, well, that little code here would run like on all these different kind of backends, and it's under the hood, it would do some performance optimization to leverage shared memory, register queue, and all these things that's done for kind of under the hood, and well, just make the code to run as optimal as possible on, well, different type of hardware. So regarding AMD GPU.jl specifically, so we kind of start the project and we have access on Lumina for not so long to do some proper scaling, but that's the status. So the AMD stack in general is not as mature as, for example, the CUDA stack, but AMD, or like Julia, does pretty well in that thing, because basically we get with AMD GPU for memcopy or diffusion kernels, we got the same results as HIP C++ code. So, well, we are there, and I mean, that's really that was a really great achievement, especially that we kind of pretty much refactored AMD GPU.jl like a couple of months ago. Then, well, that was on a single device or single GPU, but now we want to scale up. So we want not to use one GPU, but thousands of GPUs. We need to use something like, well, we use MPI here, and there we also developed something that's called implicit global grid to, well, make the distributed domain decomposition. And so if I take the same code as before, I now use implicit global grid, and I only need to call 3 functions to make that happen. So I need to initialize my global grid in the main part of the code. Then I can make an update halo, so exchange the internal boundaries of the array H that I need to, that basically my physics don't know that they're cut into pieces, and at the end just tear down the MPI and the implicit global grid. And on top of that, we introduce something so we can even hide computation behind communication. So it would make these fancy things such that, well, basically you can scale up to, well, you can hide the latency of the communication if you have like some networking thing and like the standard issue when you scale up to many, many processors. And with this approach, we get like super good parallel efficiencies. So that's kind of increasing. So that was on NVIDIA GPUs, and that's on AMD GPUs. So up to 2,500 GPUs from running a local problem on one GPU and then going for a 500 times bigger problem on 500 GPUs. We only lose like 3% of efficiency with the whole machinery, leveraging a good part of the machine. And that's achieved like in the timeline of the profiler. For those who are familiar with that, well, basically these little dots are the kind of MPI communication and all what's related to exchanging the internal boundary. And then we can like hide them behind computation of actual physics that we would anyway to have to perform. And the last little super cool bit, and I mean, that's really where I guess at least since a couple of months now, I really sell this as like, that's really where Julia stands out in general for scientific computing as we do it, is that the stack is differentiable. And that's really a big thing because other languages, like it's really, it's not there, or it's a pain, or it's expensive because you have to buy licenses for all software. And so basically now, if we want to get the gradients of those kernels, we just kind of pass this, so the gradient argument in the kernel call, and I'll initialize some shadows and then say that, well, now we'll store or accumulate the derivatives basically of this term with respect to other terms in those bar terms. And this can be, like, again, if you followed or watched back the workshop from Tuesday, this can then be readily used to combine to get gradient and make gradient descent and optimize for a parameter in those things. And really the cool thing, so here I also kind of kudos to like Enzyme and people who are working on that and also who are very helpful. So the performance is actually pretty good. So Enzyme runs on GPU, it would analyze the GPU code and create for you a new GPU kernel that would again run on the GPU, and all this is done automatically. And the cost for now, at least, is only kind of, so the effective memory throughput, so that's kind of the performance we get running the forward pass of the kernel, and then the enzyme generated kernel that accumulates the gradients and derivatives runs at 50% of the forward pass, but which is great, can be better, but it's already super. And why it doesn't matter so much is that the adjoint solve is linear, so we need much less iteration, so much less call to that function, and at the end it's kind of negligible compared to the forward solve, which is really a big thing. So yeah, well, with this I'm done, and I thank you for your attention.
Thank you, Ludovic. We have time for a few questions right now. Go first. Microphone will be there in a second.
Just a quick problem. What are you doing on slide 10? What's your problem that you parallelized?
Oh, here it's the thermomechanical 3D Stokes problem. So kind of incompressible Stokes with like nonlinear viscosity that's coupled to temperature source term, like shear heating and nonlinear viscosity in the Stokes. So 3D Stokes, double two-way coupled to temperature.
Hello.
Hey.
Nice to see you again. Can I ask you a question about absorbing boundary conditions? I saw an issue I think it was parallel stencil. I don't remember if it was parallel stencil or implicit global grid.
Parallel stencil.
But it was talking about using PML boundary conditions on wave equation propagations. Do you guys have any update on that?
Yeah, so somehow the person that opened that issue didn't...
Right?
Sorry?
Disappear, right?
Well, yeah, it's kind of, apparently it was ready, but I never get the pull request. And now I have there's a student at ETH who made like some brain MRI using parallel stencil in the wave physics group, and he has it. And I guess we'll can have his development. So it's there, or it soon be there.